Okay, let's finish this sample final. We left off on problem number 6. So we're given this function, 2x squared minus 1 over x squared minus 4x minus 21. Find all points of discontinuity. So let's try factoring the bottom. So f of x would be, let's leave the top the same. The bottom, if we factor, that would be what? Negative 7 and plus 3. X minus 7, x plus 3, like that. Okay, so we know that this is discontinuous when x is equal to 7 and x is equal to negative 3. Okay. Use intermediate value theorem to verify that f of x has a 0 on the interval 0 to 1. Okay. What is this trying to say? Remember what intermediate value theorem says? Let me briefly review it over here. F has to be continuous, that's key. Okay. There's some point A, x is A, and x is B, okay? And f of A, f of B, okay? Because it's continuous, then for some point in between, the function has to cross this in-between point at least once. So it could look like this, it can look like this, or something like that, okay? So that's what intermediate value theorem says. As if f is continuous, and in some like interval a and b, where a is less than b, and then the function has values f of a and f of b at those points. Since f is continuous, let's say this point is between these two y values, f is continuous, so the function has to cross this point at least once. Okay, that's what intermediate value theorem says. Okay, so in this interval, well, first of all, we have to show that f is continuous. We just said, because in part A, we found it's discontinuous at x is negative 3 and x is 7. So we can say first, f is continuous on the interval 0 and 1. That's important. Okay? Okay, so now we just have to make sure that, or even we can say this, inclusive, okay? We can say f of 0 is equal to what? We plug in 0, we would get minus 1 over minus 21, so it will be 1 over 21, okay? F of 1 is what? It would be 2 minus 1, which is 1. And then we would get 1 minus 4 minus 21. So negative 3 minus 21, that is negative 24. Okay? This is greater than 0. This is less than 0. Okay, we said it's continuous. We showed that in this interval, there's one of the endpoints, f of 0, doesn't have to be endpoints, but f of 0 is positive, f of 1 is negative. Therefore, by IVT, there is at least 1 0 in the interval 0 and 1. Okay? Next, find the equations for any horizontal and vertical asymptotes of this function. Well, we found that it's discontinuous there. There's no removable discontinuity, so these are asymptotes. So vertical asymptote, x is 7, x is negative 3. Okay, how about horizontal asymptote? Okay, remember for these rational functions, we do the degree test. Degrees are the same, so we take the ratio of the leading coefficients. So it'll be y is equal to 2. Okay, let's move on. Not bad at all. The key here was the hard part of this problem was intermediate value theorem. True, false, and we have to explain our answer. Unjustified answers will not receive credit for whatever reason. Okay. Let f of x be tangent x. By the mean value theorem, there exists some c in the interval 0 to pi such that f prime of c is equal to 0. Okay, remember, one of the conditions for mean value theorem, I don't even need to remind you what it is, per se. One of the conditions has to be f needs to be continuous. Okay? In this interval, 0 to pi, remember how the tangent looks? At pi over 2 and minus pi over 2, at odd values of pi over 2 even, there's asymptotes. Okay, so at pi, and this will be 3 pi over 2, there'll be another asymptote there. It looks something like this, remember? That's how the tangent looks. Okay, so this is, we know to be false. F is not continuous in the interval 0 to pi, so mean value theorem can't be used. Okay? As simple as that. Assume the half-life of a certain radioactive substance is 200 years. If we begin with n grams of the substance, then after 600 years we have 1 over 8 times n grams. Okay? So you just have to remember what half-life is. After 200 years, the initial value will half. So you can even write like this. After, this is the years, this is the grams, okay? So when we start at 0 years, we have n grams, right? If we begin, so 0 years, n grams. After 200 years, it will be n over 2, or half. That's half-life. So another 200 years, so 400, we get n over 4, another half. Half times half. So 600, it will half again, n over 8. So 1/8 true. Okay? That's one way to show it. If you like to have formulas, you could just have half to the k times n. K is equal to what? 600 over 200 equals to 3. So it would be 1/8 n. Same thing. Okay? Either way is fine. Okay. Capital F of x is sine cubed x over 3 plus 10 is an antiderivative of sine squared x. This I can tell is false right away. Okay. How can we check? Well, if we differentiate, antiderivative, if you differentiate, you should get back the original guy. Okay. So if we differentiate this, you should get back sine squared of x if it's true. Okay. If we differentiate this, it will be sine squared x times cosine of x. Okay. We need the chain rule. So this is not equal to sine squared, but this is false. Okay. This one you actually need to use, you learned this in Math 2B, the half angle formula to solve it. All right, let's move on. Pebble is dropped into a calm pond, causing ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 2 feet per second. So they give us a rate, let's write it out. dr dt is 2. When the total area of the undisturbed water is 16 pi, A is 16 pi, let's write that. At what rate is the total area of the disturbed water changing? So we're interested in dA dt. Okay. So they give us these two. We're interested in this. So maybe let's write out the formula for area. Okay. This is what? It's a circle, right? What's the area of a circle? Pi r squared. Okay, we want dA dt, so let's differentiate. It'll be 2 pi r dr dt. Okay, so we have dr dt. We don't have r. So how can we get r? Well, we just use this over here, okay? So let's solve for r. 16 pi is equal to pi r squared. So r is equal to 4. As simple as that. Okay, so we have a r, we have dr dt. We can find dA dt. It'll be 2 pi times 4 times another 2. That is 16 pi. We need units though. It even says remember to include units. What are the units of area changing with respect to time? Area would be feet squared. Time is seconds, so feet squared per second. Very easy related rates problem. This is probably an optimization problem now. According to the postal regulations, a carton is classified as oversized if the sum of its height and girth, which is the perimeter of the base, exceeds 108 inches, 108 inches. Find the dimensions of a carton with a square base that is not oversized and has maximum volume. Okay, so how do we work this out? What are we trying to optimize? What are we trying to maximize or minimize? Okay, we are trying to maximize volume. So what's the equation of the volume? That might be helpful to write out. V is equal to what? Okay, how do we find volume? It's area of the base times height. This is a square base, so if the base, let's say, is x, okay, x squared h, let's say. Okay, that's volume. We also probably want a secondary equation. So in these types of problems, it's usually a primary equation, the one that we're trying to optimize. The secondary equation, most of the time, in order to help solve for one of the two variables. So like here, there's two variables. We like to get it in terms of one variable. That's the only method you know in this class. So we need another equation to make this in terms of x or make this in terms of h. Okay, and in fact, they give us if the sum of its height and girth exceeds 108, it's classified as oversized. So that's probably the equation we want to use, okay? So let's write it as 108 is equal to height, the sum of its height and girth, right? So height, h, plus the girth, the perimeter of the base. What's the base? It's the square base. What's the perimeter of the square? It is just 4x, right? Let me draw a square. If this is x, the perimeter is just the length of all the sides, right? X, there's 4 of the x's, so 4x, okay? So we can rewrite volume now as, well, we can solve for h here. You can solve for either x or h, doesn't matter. Let me just solve for h. H is equal to 108 minus 4x. So we can write this as x squared times 108 minus 4x, okay? We can even distribute. Okay, this is v. So now we want to maximize volume. So how to do that? We take derivative. dv dx would be what? This would be 216x minus 12x squared. We're going to set it equal to 0. Okay, that's how we optimize. set derivative equal to 0, meaning it's going to be, we set this to equal to 0 because that means that there is a max or min in the volume. Okay, remember that? Okay, so let's solve for x. Okay, let's try to simplify this a little bit. If we divide both sides by, is it divisible by 12? Let's divide it by 4 first. I'm going to do it step by step. I'm going to do it slowly. If we divide this by 4, what would that be? That would be 54, correct? Okay. Does this help us out? It does, because now if we divide by 3, we would get what? So here would be a 1 and a 8, 18, right? I'm doing it slowly. I'm doing this in my head. But now I'll calculate this. So now we can factor here. So it'll be x times 18 minus x is equal to 0. So we have critical points that x is equal to 0 and x is equal to 18, okay? Okay. If x is 0, we won't have any girth. So there's no carton at all. So we're not going to use that. We're going to use 18. Okay. So what are we asked? We're asked to find the dimensions of the carton. Okay. So we found one of the dimensions. The square has side 18. Okay. So the height, 18, by the way, don't forget inches, units, which is inches, okay? Heights, we can just plug into here. We can be right at the edge, and that will still be okay, okay? The edge meaning this limit of 108. It will just be 108 minus 4 times 18. What is that? That is what? 108 minus, is that 64? My bad, it's not 72. Okay, so then that would be what? That is 36 inches, I believe. Let me check if I did this correctly. Yep. So the square has side 18, height is 36 inches, okay? That's how we solve this problem. So to recap once more, we're trying to maximize volume or to optimize it. This is the formula for the volume of this carton. Volume is always area of the base times height. The base is a square. So let's call the side of the square x squared h, okay? We're also given that there's this rule where the height and girth, the sum of them cannot exceed 108. So that's this guy over here. We solve for h, we plug it in here to make v in one variable, and then we differentiate. We solve for the critical points. We don't take x as 0 because that won't be a carton then. We take x as 18, which is the side of the square. We can find the height by plugging in the value of x there. So height was 36 inches. Okay. Okay, let's do the last problem. For the function of this guy, answer each of the following. Find all intervals on which f is increasing and all intervals on which f is decreasing. Okay, so how do we do that? We do the first derivative test. F prime would be 12x cubed minus 24x squared plus 12x. Okay. So we can factor out a 12x. It'll be x squared minus 2x plus 1. Okay, we set this equal to 0. Okay, this we can factor. Okay, so we have critical points at x is 0 and x is 1. So we do our first derivative test. Okay, we plug in a number less than 0, so we can plug in a huge negative number. This would be negative. This something squared is always positive, so this would be negative. The sign would be negative. Plug in something between 0 and 1, like half. This is positive. This is always positive, so it'll be positive. Plug in a number bigger than 1. We can plug in a huge positive number. This will be positive. Again, this term is always positive, so the sign would be positive. Okay. Okay, so we can say that f is decreasing in the interval negative infinity to 0, and f is increasing on the interval 0 to 1 and also 1 to infinity. Okay, at exactly 1, it's not neither decreasing nor increasing, okay, because the derivative is 0. Okay, so at exactly 1, it's neither increasing nor decreasing. So that's why I wrote it like this. Find any local max and min. Well, we can use what we did up here, this first derivative test, to find this answer, okay? Local max min. Well, there is a local max or min when the derivative changes signs. That only happens here. So we know that there's a local, is this a max or min? Derivative goes from negative to positive. We know this is a min. Local min at x is equal to 0. The value would be, so let's write it in a coordinate. 0 comma, what's the y value? We plug it back into here. Don't plug it into f prime. Plug it in here, because this is asking for local max min of f. It's not clear for that. It will be 1. Okay. This is a min. Sorry. Okay, that's a local min. There's no local max. Okay. Find all intervals on which f is concave up and all intervals on which f is concave down. That we need second derivative test. So let's just use our f prime here from this point. F double prime would be, what's 12 times 3? That's 36x squared minus 48x plus 12. Okay, we set this equal to 0. For the second derivative test, we could factor out a 12. That would be 3x squared minus 4x plus 1 is equal to 0. We can factor the inside. Most likely, will have to be like this. Okay, so we have critical points at x is 1/3 and 1. Okay, so now we do our second derivative test. So we plug in a number into f prime that's less than 1/3, like 0. We see that the sign is positive. Okay, plug in a number between 1/3 and 1. For example, you can plug in like 0.9. Okay, this would be either would it be positive? Would it be negative? Okay, 0.9 squared. It's actually smaller than 0.9. So I had to be precise. You can plug in half even. I believe it's negative, but okay, let's just plug in half. If it's half, then this is what? 36 divided by 4, which is 9. 9 minus 48 divided by 2, which will be a negative number. What's 48 divided by 2? That's 24. We just said what this was. 9 minus 24. 9 minus 24. What is that? That should be 15. Negative 15. Negative 15 plus 12, that's negative. Okay? And then we plug in a huge positive number, like it doesn't matter, 100. Actually, we could have just plugged in here. I don't know why I went up there. We can plug in here, it's easier. Plug in a huge positive number. This is positive. This is positive. It'll be positive here. Okay? Let me redo it here. Okay? Plug in 0, you could plug it in there. That's fine. Over here, you can do the same thing. This would be negative. This would be negative. 2 negatives make a positive. Correct? You plug in like half. This guy would be negative. This guy would be Yeah, this guy is positive, this guy is negative, so this would be negative. And then this one plugging a huge number, both positive, positive, okay? So, concave up, when the second derivative is positive. So it's from minus infinity to a third, union 1 to infinity. And then it's concave down when it's from 1/3 to 1. Okay? Points of inflection, that's when the second derivative changes sign. So it will be at both these points, so 1/3 comma something, 1 comma something. Okay, so we just plug into here. Okay, let's plug in the 1 first. That'll just be 3 minus 8, which is -5, plus 6, which is 1, plus another 1, that should be 2. So it should be 1 comma 2. Okay, and then the tough one is plugging in 1/3. Okay, I'll save steps here. I'll let you do the plugging in. It's technically not a nice problem on a test, but if the key is right, it'll be 38/27. Okay. Graph function. This is curve sketching. Okay. Okay. So we know that there is a min. Okay. Well, we know where f is decreasing and increasing. We know when it's concave up, down. We even know where there's a local min. Okay. So let's use these critical points as guides for our sketch. Okay. So everything is actually positive, so I didn't need to draw all this over here. But it's 0 and 1. And 1/3 and 1. So okay, this is half, this is 1. Okay? Or you can even do a 1/3 here. It doesn't need to be to scale. This is just a sketch. Okay? So we know f is decreasing from -infinity to 0, and then we have a min at 0. Okay, so it'll look something like this. We even know the min value. Okay, because we found the min to be 0, comma 1. Okay, and then after 1, after 0 it increases. Okay. At 1, it stops, but this is just sketch, so you can't tell. Okay, so now let's look at points of inflection and concavity. So everything here was concave up, right? At 1/3, it's going to change to concave down. Okay, and then back at 1, it's going to change back to concave up. Okay, but remember, after here, f is always increasing for the most part. Okay, so how do we draw this to be, this is right now concave up, how do we draw it to be concave down but increasing? It looks something like this. Okay, and then it'll be concave down increasing until some point here. Okay, and then it'll be concave up again, and then it's still increasing. Something like this. Okay, this is just a rough sketch. Okay, and that's it for this exam. It's not too bad at all, so hopefully this was helpful, and I went quite slow on some of the problems even. So hopefully this video helped you out in some way. If it did, please hit that like button, and please subscribe to the channel also to see more videos like this.